Thank you very much for the introduction. And, it's really my great pleasure to come to South Korea for this Benjamin professorship. And also, it's my great pleasure to have this opportunity to give some lecture on some old stuff and also on some new stuff. About those papers mentioned, I'm very grateful to Physical Review B, because I have a lot of weird paper I don't know where to send. But the Physical Review B is a very, inclusive and tolerant. So whatever I send to them, they can publish it. So because those papers really is have physics, has some math, it doesn't fit anywhere, but it fit Physical Review B. So I'm very grateful for Physical Review B. And so in this full lecture, basically I'm going to discuss some recent idea of dealing with so-called gapless quantum matter. I've been working on topological order, which is the gap quantum matter, for maybe 30 years. I thought I should finally graduate, maybe start
recording in progress.
One. And but the gapless one is difficult, and but recently we have some ideas, and so I'm really planning to talk about those ideas. But to prepare for that, there's a long preparation for the gap quantum matter, and so eventually I hope we will get to this some idea for the gapless one. So today I will start with something very simple. This symmetry breaking, some really old stuff. It's also my recent realization that even symmetry breaking state we don't understand very well. So the quantum system is really very complicated. So what is the many-body quantum system? This is for the mathematicians. So it's basically it have a Hilbert space, we have a Hamiltonian, and the Hilbert space have a tensor product decomposition, which is we have a small Hilbert space on every side. The tensor product give us a total Hilbert space. And then we have this wave function, and also we have a Hamiltonian. But the Hamiltonian is a sum of so-called local terms. This Hx only act on the one side or act on the neighboring side, some kind of local Hamiltonian. So this kind of standard stuff. And then we have this, for example, of that will be like a one-dimensional system. They live on the ring. We have a spin 1/2 per side. That's two-dimensional Hilbert space per side. We may have this transverse field Ising model, where the X, Z is a 2x2 matrix. But we notice that the whole quantum system of Hamiltonian is a 2 to the L by 2 to the L matrix. So I don't know whether my animation would complain, how come product 2x2 matrix become 2 to the L and 2 to the L? But certainly, the physicists, we know that kind of sloppy. This Xi really means this huge operator with a canonical product. And it's important if you want to write a computer program to construct this big matrix and diagonalize it. So here's what we do. Right now, the computer is very convenient. There's a lot of free software. For example, if you want to pay, you can use the MATLAB. If you don't want to pay, you can use the Octave. And the canonical product have a function. It's this tensor product is a canonical product of 2x2 matrix. And you can times a lot of identity matrix to get a big 2L by 2L matrix. And there is also sparse matrix. So this SP is a sparse. So actually you can construct a huge matrix using sparse storage, and so you can compute a very big matrix. So just maybe maybe less than 20 line, you have a program to do this, and you get this spectrum. I hear the spectrum for the first 100 states for different ratio of H over J. The point is that from the spectrum, this is like doing experiments. We do the experiments, these are our data. Then we see something. We see, well, there's an energy gap here. There's a gap phase. Then there's another gap phase. And in the middle, looks like there's a closing of energy gap. Actually, there's still gap, you know. Again, the mathematician may complain that, but this gap goes down like 1 over L, so scale down to 0. So we say this part is gapless, and this part is gapped for some reason. And so there's a phase transition when H over J equal to 1. So this is a thing we want to study. That there's a gap phase, there's a gapless phase transition point. We want to understand them. And certainly there's an issue that you know, why we call there's a phase transition at H over L, H over J equal to 1, because everything is smooth, all the curves are very smooth. Certainly we know that the key point is that in a thermodynamic limit, the curve may develop singularity. When L go to infinity, there's some singularity. For example, here I plot this difference of the first and the second level in the spectrum. And when L go to infinity, actually here only 13, you can see they develop a singularity right at 1. So in general, the notion of a phase is actually is something like to define quantum phase, we need to define phase transition first. So what is the phase transition? The phase transition are the line or surface such that the average of a local operator have a singularity as function of some coupling constant in the Hamiltonian in the limit of a infinite size system. For any finite size system, the function all kind of a smooth function, no singularity, but at the infinite, if for large system, there's a singularity. So this is a phase transition. Then the region separated by phase transition line will be called the phase. So maybe so for the region connect in the same phase, we can deform the system into each other so that the average of any local operator are smooth. There's no singularity. So that's kind of a general way to define phase and phase transition. Then it's come to some more fundamental question: is that why we have a singularity in the thermodynamic limit? So what is the mechanism? And so then it looks pretty non-trivial that the spontaneous symmetry breaking actually is a mechanism which causes the singularity. You know, so if you just look at the data, you know, there's some similarity. We don't know what's the reason, and so it looks pretty mysterious. Then this insight, yeah, the symmetry breaking is a mechanism causing singularity is a pretty non-trivial insight. Okay. Yeah.
When you say local operator,
yes.
When you say local, especially local or
Spatially local. Always spatially local.
If so, standard phase ferromagnetic, usually you have triple zero singularity. Really?
Yeah.
So this case.
I think so. It's yeah. It's this. This G actually, this G can be external magnetic field. So the G coupled system uniformly. So you can view G as external magnetic field. And then when you turn the external magnetic field, then you can measure local spin as a response. Then in the paramagnetic phase and the ferromagnetic phase, this response to the uniform magnetic field will be quite different. So that in that way, so therefore the average of a local spin operator have a non-trivial response to the external uniform magnetic field. So this may signal this ferromagnetic order. So it's kind of in this. But there's a important thing is that if any local operator have a singularity as a function of some coupling constant, then we will see there's a less phase transition line. Because it's possible that certain very special operator don't see the singularity. But some other operator will see singularity. Oh, that also count. Yeah. Yeah, feel free to ask any questions. So we should have discussion. Yeah.
Can I ask a question? In the Zoom?
Yeah. Okay.
Oh,
please.
Oh yes. So are you saying that the ground state energy density can also is not an example of average of a local operator?
No, ground state energy density is a example of a local operator because the ground state energy density is average of this HX. Yeah, so HX is a local operator.
Okay.
So, yeah.
So you're suggesting that some local operator cannot detect it in certain cases, but this ground state energy density is always possible to detect. Is that what you're saying?
Oh, that's a very good question. Maybe not. I wonder whether there's a very specially designed system where ground state energy density you don't see any singularity, but some other operator you see singularity. I don't know the example, but yeah, I do worry about that possibility. You know.
I see. Thank you.
Yeah.
Could we apply the same definition to the non-local operator? For example, Wilson service, is there any issue?
Yeah, that's the issue. That's something I don't know how to answer. You know, it's very important that the quantum system have locality respect to this tensor product decomposition. So what do you mean local? Local actually is not concept of linear algebra. It's a concept of a tensor product decomposition. And this local respect to certain tensor product decomposition is very, very important. So because we define Hamiltonian as a local Hamiltonian, then to detect phase transition, we also use the same concept, same tensor product decomposition, same concept local operator to detect phase transition. And yeah, actually these two questions really, really interesting. If you have you use one set of tensor product decomposition to define local Hamiltonian, and using another set of tensor product decomposition to define some other local operator in other means, like in momentum space. I don't know the answer, but this I haven't thought about. But this should be really interesting. But I imagine a lot of the things I said won't apply. Because here is very crucial. Yeah, thank you for the question. We choose a particular tensor product decomposition, using that to define our localness, and using that to define entanglement. So everything coming from there. So this tensor product decomposition is very, very important.
Yeah,
but changing that will be a lot of fun. But I don't know what is physical consequence. It will be very interesting.
Sometimes we consider the confinement or deconfinement by the Wilson surface operator, but it's non-local. I think it does not have a tensor product.
Yeah, no, that one works with this framework. Yeah, yeah. I will come back later maybe for this extended operator. Yeah, that will play important role.
Thank you.
And so indeed, a certain non-local operator can also be used to detect phase transition. But here, as a definition, the phase transition is defined as those detected by any local operator or all the local operators, something like this. Then sometimes non-local operator is more convenient to see some other structure. Yeah, this is really important. Okay.
Sorry,
so those are really just a very yeah, please.
So if you have this this tensor network, do you assume certain dimension data? So in a tensor network, you can tell which dimension it is. Do you assume
the
that?
dimension? Again, it's a dimension very important. And let me see whether So you can see, in a tensor product decomposition, I try to define the localness, but the localness have this meaning as H act on the single site or act on neighboring sites. And I did not define what neighbor means. So mathematicians should also complain. What do you mean by neighbor? So actually here, I already assume this side is a part of a graph. So we already have a meaning of which side are neighbor to each other. And this neighboring side, this concept, define the dimension. We know the physics depend on dimension a lot. 1 dimension, 2 dimension, 3 dimension have very different physics behavior. But this dimension is defined by this again, the localness and the concept of neighboring. I think nowadays some people study, suppose we have some fractal, some tree like of a graph, So that is we modify the definite localness, so it will be very different physics. Yeah, any other questions? Yeah, either on-site or Zoom. That's great. Yeah, we have some discussion here. Okay. So the spontaneous symmetry breaking actually is a mechanism to lead to this singularity and the phase transition. But however, our understanding this mechanism is very, very strange. In the textbook, everything looks natural and standard. But actually, you're thinking about it is very, very strange. Because our understanding for spontaneous symmetry breaking is not through this pure quantum theory. It's through approximation or this variational approach. If you do not make any approximation, stay with the exact quantum theory, this is what you see. It's hard to see spontaneous symmetry breaking from this picture, But however, if you do an approximation, then we have a theory of a spontaneous symmetry breaking. So spontaneous symmetry breaking actually is a theory for the approximation, not for the original quantum system. If I put that in the extreme way, okay. So the more standard way to say that actually we have this variational ground state. So this phi is variational parameter. Then we compute its energy as a function of this variational parameter. And then this function is a smooth function. This function as a function of a coupling constant G and the variational parameter phi is a smooth function. But the ground state energy is the minimal of this smooth function. And the minimization causing singularity. So we have this minimal splitting as we're changing G, the minimal from single minimal is split into 2 minimal. And we have minimal switching. One minimal switch to another minimal as we're changing G. So this became the standard. It's a continuous transition and the first order transition. One is the minimal splitting for continuous transition, and the minimal switching will be the first order transition. And so it's this is standard explanation of a symmetry breaking theory, but it is not a theory for quantum system, but a theory for some variational approach. And for example, we can have for the Ising model, this transverse field Ising model, we can using superposition spin up, spin down on each side, and the tensor product of that to obtain our variational wave function. And here I just want to introduce an example. These are product states. On every side we have particular states, and the many-body state is a tensor product of a state on each side. This became a product state, or the simplest states. And certainly the true ground state is not like that. But we're using this because we can compute this average energy easily. For other tri-wave function, too hard. And so this became kind of standard. But also it's kind of a trap. That is in condensed matter, we kind of study a lot of the tri-wave function of this type. So it's a product states. So therefore we miss this highly entangled states. So we miss this topological order. And but we'll explain that later. But anyway, so if you do this phi as a certain parameter, we can see that as a ratio of H over G changes. Sometimes we have 2 minimal, sometimes 1 minimal. So that's a standard symmetry break transition, but only for the product states. That's one thing I want to emphasize here. And also from here, this is also standard stuff. We have this we can have this case for London theory, because under this symmetry transformation, which is spin flip, will not spin flip. This is that's a Z is a Pauli matrix Z. which really flip x to minus x spin. And then this then and the symmetry transformation, yeah, and the phi go to minus phi, and these two states have same energy. And so if phi to 0 happen to be the ground state, then that's symmetric phase because that's the environment under this symmetry transformation. However, if phi is non-zero, it's a ground state, then that's symmetry breaking state and have degeneracy. You know, phi and minus phi both have a same energy. So this became a more standard symmetry breaking transition, and we have the Ginzburg-Landau potential to describe this transition, and we have all the parameters. So those are standard stuff, but the message I want to make here is that it's really a classical picture. Somehow it's very hard to understand the symmetry break transition in quantum theory, in quantum setting. So we turn quantum theory into classical theory and minimize this classical parameter phi and then to get this symmetry breaking phase. And the reason this is classical theory because in this setting, we even get a phase transition at the 0th dimension. You know, we can minimize, this works even in 0th dimension. And we know that in 0th dimension, we don't have phase transition. And so this really approximation. And so another thing I want to emphasize here, again, it's very standard, is that in this version approach, we can view this upspin as a vacuum, as a reference, the downspin as a presence of a particle. So actually, this tensor product state have another way to look at it. It's a superposition of all configuration of particles. And so it's a quantum liquid. You have a particle have all kind of distribution and the superposition of all distribution. And this is a notion for a condensation, a notion of quantum liquid. So therefore, this is in the symmetry breaking phase, we have so-called condensation of this downspin of this particle. And the condensation actually is so simple, but it's play very important role, even in the very, very fancy setting. So we'll introduce this here. Later, we will see a lot of mathematics about the condensation. It's a very fancy setting. Okay. So now let's consider a little bit more non-trivial example, not the Z2 symmetry, but for arbitrary non-abelian group. And then in that setting is that the Hamiltonian have a symmetry G, and the ground state may have a smaller symmetry. Yes, please.
Yes. So you mentioned that the symmetry breaking picture can be understood as a classical physics. But then you said this condensation picture. So condensation picture is probably better to be understood in terms of this quantum mechanics. And is there a simple or intuitive way to connect these two parts?
Thank you. This is a very good question. You know, certainly there's I try to emphasize that the symmetry breaking version of wave function is give us a classical picture. And but the condensation superposition obviously is some quantum concept. But actually, let me see what I say. Yeah, what I really want to say that actually this condensation condensed state is a classical state. It's precisely because this condensation state is a product state on each side. So so in some sense, this condensed state is I will discuss later, it's a really shorter entangled, actually no entanglement.
No entanglement, right.
And so it's very classical. So a little bit kind of funny, that is we have a lot of quantum physics, superfluid, all that.
Right.
But if you think from entanglement point of view, even superfluid is a classical state. It's an unentangled state.
Right.
The first time we really encounter a highly entangled state in the quantum Hall effect. So like a crystal also kind of like a unentangled states, at least in ideal situation. But this again, this is a very good question. Okay, so so the point is that the ground state have a smaller symmetry, but our Hamiltonian have bigger symmetry, and the ground state generally is this quotient, the number of elements in the symmetry group divided by number of elements in the subgroup. And then we have the other parameter is that some operator which transform non-trivially under this symmetry transformation and the phase transition from order parameter 0 to non-zero, that's a phase transition. And here I want to emphasize a point is that from this picture, we see that the continuous phase transition really caused by this order parameter from 0 to non-zero. So this kind of change usually led to the ground state have a symmetry group G1, G2. And the G1, G2, the symmetry, the difference of G1 and G2 is because this order parameter become non-zero. So that's implied that the G1, G2 have this group subgroup relation. So that's one way to summarize the Ginzburg-Lamont theory. We may have a continuous phase transition between two phases with a different symmetry if these two phases, the symmetry group, these two phases have a group subgroup relation. That's certainly the first point in the Ginzburg-Lamont theory is that the different phases are labeled by the different symmetry group of that state. And we can have a continuous phase transition if symmetry group have a group subgroup relation, then these two phases can have continuous transition. So that's these two things kind of summarize the Ginzburg-Lamont theory. And then we can do this, yes. Yeah. 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 No, I cannot. Here I should say we all consider finite symmetry. But continuous symmetry actually is a forbidden topic in my talk. It's a very different situation. And so for simplicity, I will limit myself to finite symmetry only in this series talk. But continuous symmetry certainly is a very important, very relevant. But one need further development to include to apply the picture I described to continuous symmetry. And you will see that the continuous symmetry and the finite symmetry somehow behave very differently. And so actually this is a very interesting, that's one of the insights we learned from this way of thinking. Is usually we think continuous symmetry and finite symmetry as something similar. And but in the quantum system, they are really very different beasts. Yeah. And I think classically maybe they are kind of similar, but quantum system, they can be quite different. Yeah.
Can I ask a question?
Yeah, please.
Sir, I just want to understand the last statement from the previous page.
Yeah.
The group subgroup relation. Are you saying that if G1 and G2 does not satisfy the group subgroup relation, however, if they share the same subgroup, that means you can go a two steps transition from one to the other, but
yes,
not in one step. That's what you're saying.
Yeah, that's a standard picture. Yeah,
I see. Okay,
but this picture maybe some. Well, yeah, that's a standard property line. Yeah, that's the. Okay, so let's consider an example of S3 symmetry. And S3 is the simplest non-abelian group. Is kind of permutation of three elements. This 1, 2 means exchanging 1, 2. 1, 2, 3 means a cyclic permutation through 1, 2, 3, and things like that. And it have a subgroup of a trivial subgroup. The full group also is some subgroup. And we have Z2 subgroup and the Z3 subgroup. Okay. And then actually this S3 have a two representation. One is a one-dimensional representation we call A1. Another is two-dimensional representation we call A2. So we say the phi and the big phi is these two representation. Then the little phi is that under exchange and this like parity. this one to exchange like parity. And under parity, the phi change to minus phi, but under cyclic permutation, little phi don't change. So in some sense, a little phi like a pseudo scalar. It's a changing sign under parity, but do not change sign under rotation. And the big phi is like really like a vector. That's so one to exchange is really like this poly X operator and this cyclic permutation have this fix. Okay, so that is so the big phi is complex. Okay, then we can use the little phi and the big phi to build the Ginzburg theory. It's rather complicated because I want to get the phase diagram which contain all the phases. It turns out that we have to really introduce a lot of terms, and so this part is kind of like a standard Ising model Ginzburg theory, phi-4 theory, and then remember this big phi have this order 3 rotation. So big phi cube is a symmetry. It's environment under this cyclic permutation, but they are not environment under exchange parity symmetry. But then we have this phi 1 plus phi 2. That's two components of phi. The parity exchanging phi 1 and phi 2. So this combination is symmetric. So I have the cubic term. And then we have some term which mixing the little phi and the big phi. So actually, you just from symmetry you can write down this operator, and then we write a program to do this phase diagram. Just trying to find the minimum of this, and then to get this. Then we send all the 4 phases are there. Okay. And but however, there's something want to emphasize that you can see this Z1, Z3 have a group subgroup relation. So from Ginzburg theory, it should allow the continuous transition. But actually, no. Z1 is here. You can see the first order transition. The jump. One say why don't see the continuous transition? The reason is very simple. Use a cubic term. Z1, Z3 transition involving this big phi order parameter. The big phi order parameter from 0 to non-zero. But the big phi have a cubic term. Whenever order parameter have a cubic term, then we don't have first order term. We don't have continuous transition. It's always the first order in the Ginzburg theory generically. So that's a little bit surprise because but it should be standard. Whenever you have cubic term, you don't have a continuous transition. And so I start to wonder what are they learning from textbooks. These standard party lines, group subgroup relationship, that first order continuous transition, but we don't have. And this is what happens. And similarly, S3 to Z2, these are symmetry of ground state. Again, this change also have group subgroup relation. Again, this involving the big phi, that's also first order. But and these two horizontal line transition involving little phi. Little phi don't have a cubic term. And so these two transitions are indeed continuous. That's a standard familiar case. Yeah. And also we have this
sorry. So let me try to just simply understand. So when I have G1, both phi and large phi should be condensed. So how to obtain G1?
That's both condensed. Yeah, you can see Z1 phase is here. Okay. Where the green line, red line is a little phi, and the blue line is big phi. So you can see both little phi and big phi are non-zero. Then the symmetry is broken from S3 to Z1 completely. Okay. And here we don't have a transition from S3 to Z1. Maybe we have if you choose another parameter. This phase diagram only have this alpha beta gamma to 1. With this phase diagram is a fine tune with U and V, but alpha beta gamma equal to 1. And this whole term is also chosen to have a unit coefficient, some special slice in the parameter space. And but here, we don't have S3 to Z1, but if you do have that, this transition should also be first order. because that's involving cubic term as well. And we have a direct transition from Z2 to Z3, but this transition is the first order. Then it's okay. In the first order, we can have this even but symmetry is not group subgroup relation. We can have first order direct transition. It's only this very little piece. Yeah. So this is so in some sense, even Ginsburg theory gave us a pretty rich phase diagram. And so there's a lot of question, you know. And like Z1 to Z3, from Ginsburg theory, this should be generically first order. We don't get a continuous transition. But in reality, what do we expect? I think we expect a continuous transition. That's for this. And also S3 to Z2, Ginsburg theory tell us the first order. But in reality, we also expect Z2 or continuous transition. And so there's a tension between Ginsburg theory and the real quantum story. Real quantum system may have very different structure. Yes.
Can I ask you? Right. So if you wanted to exhaust all the possibility
Yes.
in the Lagrangian, is there any principle that forbids us to use the fractional power, like phi to the 1/3 of power, for example?
Okay. Yeah. Yes. And it's kind of like this. You know, this VH phi is like a variational function, variational energy. And they are smooth function of H and phi. Because they are computed through here. Is average energy using this product states. And if Hamiltonian is local and you have product states, and this average function, I think is a smooth function of H and phi. So that's why if you do the expansion near small phi, then there's no fractional power. It's only integer power because it's a smooth function. We do this expansion. But however, your question is also very good in the sense if Hamiltonian have a non-local term, have like a 1/r, you know, of this some long-range interaction, then sometimes you could have something more singular. Yeah, when you have a long-range interaction, then the average may not guarantee to be smooth. Yeah, you may have fractional power, I think, because shorter interaction and this tensor product states, then it's a smooth function.
You say that there is no principle,
Not really principle, just our setup, our assumption. With this assumption there's always a integer power. It's you know this it's hard to say this principle because we are doing this some approximation, some variational calculation, some approximate method for quantum system, and this method say it is an integer power. It's a property of this method. You know, I don't want to call this a property method is a principle. Yeah, that's a thing. Okay. So yeah, actually this is an interesting phase diagram. And the mean field theory gave us answer. So which transition is the first order, which transition is second order, gave us a why is that. Then naturally we ask, if we go beyond the mean field in quantum system, what happens? Do you have a similar phase diagram? Do we still have continuous transition, or whether this first order transition in classically become continuous quantum mechanically? And why is that? Is that general property? What is the principle behind that? So a lot of questions, even involving this even simple case. So in the recent year, we have this tensor network calculation. So actually, tensor network calculation is a very ideal method to deal with this system, for a large system. So therefore, we consider some kind of, again, a system with S3 symmetry. And so previously I'm talking about the 1+1 dimensional quantum system. It's more convenient to talk about the 2-dimensional statistical system, which are kind of equivalent. So here I switch the gear a little bit, and we'll consider a 2-dimensional statistical system with S3 symmetry. And then we want to write down energy for this statistical system. it's very complicated. But why you go to that complicated thing? Because I want to produce all the 4 phases. Because when you have S3 symmetry, S3 have 4 subgroups. So the possible ground state have 4 possible symmetries. Then we want to produce all these 4 possible phases. It turns out that we have this pretty complicated one. So let me explain it a little bit. So here we have a theta and the phi, which is just a director, some kind of you can view this some kind of director like this. Just some vector point in the 3 directions, and then this term, okay, this whole term is we have square lattice. So this term is like the theta I and theta I plus x, they are kind of coupled together. They want to be the same, and in y direction also want to be the same. So actually, this first whole term gave us a pulse model. If j is very small, the theta is a random, you get a disordered phase. If j is big, then the theta want to be aligned, you get a symmetry breaking phase. So this is and this kind of theta already have the S3 symmetry. One is a rotation by 120 degree, another is a reflection. So that's geometric way to view this. And then we have this ferromagnetic phase and the disorder phase. Then somehow when I first heard the ferromagnetic, I mean, oh, so all the symmetries are broken. No, actually, in this case, you can see the ferromagnetic state only break S3 to Z2. So therefore, in the standard model, if you have this only first whole term only have theta, you have a pulse model, 3-state pulse model, it's only have one transition from S3 to Z2. So the pulse model describes this transition. And this transition is continuous. In the pulse model, we can do the calculation, it will show it's continuous transition. So therefore, mean field theory is wrong. Mean field theory, because cubic term is the first order, but the quantum theory is continuous. And so actually they become question, is this, what is the principle behind that? Why the mean field, the first order became continuous quantum mechanically? Do we have a systematic understanding of this? And we're thinking about it, and then we find this the Precy have a paper discussing this. Quantum fluctuation make first order transition into continuous transition, and so I think this people really know this and studied this before. So then the challenge is that using this first whole term is very simple, but we never get a Z1 states. No matter what we do, we never get Z1 state. So we have to find which way to get a Z1 states. So we pay a lot of price. Introduce another direction on order parameter phi, which is similar to theta. Introduce another Z2 order parameter like S. To get the Z1 state, it's important to get the chirality. That is, we have one vector goes this way, but another vector go like this way. Then from first to second, you turn clockwise. Or from first to second, you turn anti-clockwise. So this kind of chirality is what break Z3 down to Z2. You need some chiral thing. And so that's the reason we have these 2 director order parameter. And we have this S, just a chirality coupled to this director. So that's what's behind this design, this model. Okay. And indeed, when we do this and when we do this complex model, indeed we recovered all the phase. So this is a tensor network calculation of that model, this phase diagram. And tensor network is really, that's another thing I want to promote. The tensor network is really a very good and modern numerical method. So in this phase diagram, the phase diagram you'll see probably representing maybe one, let me see. Each step is 4 times the 10 steps, and representing 1,000 by 1,000 lattice, so million spin. Yeah, and so it take about maybe an hour or 2 hours in the desktop. You can do million spin, and but there's no other method can do this. And so actually you can get a pretty very clear phase diagram. So here this color grade is the inverse of ground degeneracy. So the white one means no degeneracy. The black one is a 6-fold degeneracy. And this is a Z3 phase. This is Z2 phase. Yeah. And here we see the direct transition from S3 to Z1 in some parameter regime. So there's some parameter regime. In some other parameter regime, and then we see this multi-critical point. This transition line shrink into a point, then we get this 4-phase meet at the one point. We have the multi-critical point. Yeah, and that's kind of interesting. And then indeed we find this S3 to Z2. That's a standard post-model transition. That's a second continuous transition. And the Z3 to Z1 also continuous. Okay. And the Z3 to Z2 to Z1 is a Z2 symmetry breaking. That's a standard async transition. Similarly, this S3 to Z3 also breaks Z2, also standard async transition. And we have a hard time determining what is this transition. It's a first order or continuous, and we kind of flip flop on this. First I thought maybe it's first order. We don't have the continuous transition. Then later we say maybe continuous. The reason we're hesitating is that it looks like continuous in some sense, but we couldn't find a conformal field theory to identify with that. So the other force transition, the numeric data is more clear, and we have a candidate conformal field theory just fit numerical data. Yeah.
Can you just tell us the horizontal axis and the vertical axis?
What
In this phase diagram?
Yeah.
What's the horizontal axis and vertical axis?
Oh, yes. And it's I think it's let me see. So the
in this plot,
J1, J2, yeah.
what
I
did
think
you plot?
It's a J1, it's a function of J1 and J2. So JC, G and JC, J and G are fixed. I did not explain this model in too detail, but very roughly, J1 is control the post model transition. J2 control this async model transition. And other term JC, J, and G are some coupling between those two parts. So this model basically is a post model combined with async model, which transition controlled by J1 and J2.
Your phase diagram calculation is
I fix the JC, J, and G to some value.
I see.
And changing J1 and J2 and the plotting. So this horizontal axis J1, the vertical axis J2.
And it's finite temperature simulation?
It's a finite temperature. You can see that the phase time only depends on G times beta. Beta is inverse temperature. So I'm plotting this.
Temperature is included
in this plotting. So if I'm plotting this beta times J1 and beta times J2. There's a number here, but I didn't write. So these two phase time have very different range. This phase time is very fine-tuned. So it's only for very small delta J. And this is for much bigger delta J.
Okay, thank you.
Yeah. So I want to really see this is a very good transition. Yeah. And maybe later I will explain this a little bit more. But here just see there's transition. And the point that here I try to say that this full transition line, we know which conformal field theory. So there's so-called minimum model, some conformal field theory describing this one. But this one we don't know. So it's I think now I'm thinking that's maybe first a continuous transition, but which conformal field theory determine that is to be determined. So actually this is a issue. Yeah. So how to determine the conformal field theory? compute the critical exponent for this transition. So I'm very surprised this is the open question. Yes, please.
So I have a little question.
Yeah.
So why are these phase diagrams independent of the relative value of x and y that you have chosen for the energy?
X, Y.
I mean, in the previous page, there were dependencies on x and y, right? And which side are coupled? So SI and SI plus X. So should it matter the relative values of x and y that you have chosen here?
Yeah.
I mean, should the diagrams depend on the relative values of x and y? Like how far?
Oh, I'm sorry. Yeah, X, Y. I'm sorry. This is unit vector. So means that we're changing by one lattice constant.
Oh, this is one.
This is square lattice. Yeah, this is U1. So this is square lattice. So it's a one. You do one. To one slice space in x direction, one slice space in y direction.
Okay.
So this x, y represent unit vector.
Okay.
Yeah. Sorry.
So, do you also, and can you go to next page? So here in both x-axis and y-axis, the beta is contained.
What?
Beta is
Beta,
included.
The horizontal axis is a beta J1.
Right.
The vertical axis is beta J2.
So
those are dimensionless parameters.
Right. So if we just move the temperature.
Yeah.
So it's moving diagonally.
That's right. If you're moving temperature but all those also changed. In the sense that I'm not tuning temperature. Because in some sense you can say I say temperature equal to 1. I'm changing those coupling constant. You can think that way.
Just I mean, for the sake of the so we do get the from S3 to G1 transition.
Yeah, exactly. We have this
by temperature moving. By temperature moving, right?
Yes. Yeah. I think we can get that. Yeah. By changing temperature, we can indeed go from here to here. It's not the direction I plot in this diagram, but you are totally right. By picking those other parameters to be certain, or coupling constant to be certain value, changing temperature can drive S3 to Z1.
Right.
Yeah. You can have that.
And nevertheless, you are not sure what type of the transition.
Yeah, we are not so sure of type transition,
right.
But we think now. So right now I'm in the continuous mode, so I think it's a continuous transition.
Okay.
But however, I'm really worried. I don't know if it's continuous transition. We should have conformal field theory describing that. This is one dimensional, 1 plus 1 dimensional system. And right now, I did not have a conformal field theory. So I'm a little bit, I could be wrong because numerical calculation sometimes can be tricky. You have very weak first order, then looks like continuous. For several years, people say that's continuous. Then later, oh, that's a weak first order. So I'm a little worried about that. Yeah. But probably not happening here. Yeah. And similarly, again, you can see the transition. So now I can this transition and maybe for someone to know what I'm plotting here is a central charge. So actually, tensor network calculation can give you a central charge at the transition. And in the gapped phase, there's no gapless excitation. So central charge equals 0. So only in the transition, you have a gapless mode. Gapless mode gives you non-trivial central charge. And you'll see the scaling from the gapless with central charge to the gap with no central charge. This width of a line depends on system size. So here I think in this graph, I'm plotting probably the system size maybe is 256 by 256. Then you have this kind of width. When the system is getting bigger, this line getting sharper. So therefore you'll see this very clear scaling. And it's a color plot. So this central charge is 1/2. It's really correspond to Ising transition. And here you also see some scaling. And the central charge is I think 4/5. So that's a pulse model transition. All mean the model. But here is central charge is it's not it's a shifting. So it's not saturated. So we don't know. Around 1 point.
喂，你好，喂，
Yeah.
喂，您好，
Yeah,
您能听
please.
到我说话吗？哎，我是那个
Yeah,
北航
I
的
can.
北航的，就是开会的就是
Hello?
您那边就是您的店在哪里啊？
I think it's you're probably in the wrong
就
place.
是还是蛮近的，是吧？啊，就是我们开会地方在那
I think the
个
chair can mute this
Yeah.
the person who will speak.
You probably joined the wrong Zoom.
Oh, but at this point, can I ask a questions?
Yeah.
Here you define you set up the phase diagram using a lattice model. I want to ask, since we already know all the, for example, the classification of all gapped quantum liquid phase, or even have a lot of knowledge about the rational conformal field theory. So my question is it possible to talk about the phase diagram without referring to any concrete lattice models and Hamiltonians? Is it possible to do a question like that?
Yes and no. I think actually that's one thing I'm going to talk about later. That is, if you know this a general theory for gap phase and a general theory for conformal field theory, then there's a way to put them together. There's only certain way to put them together. Say certain gap phase can only be connected by certain conformal field theory. So there's a lot of constraints. So actually, this is the main story I want to present, maybe in the fourth lecture.
I see.
And so indeed, but however, for the very concrete, but in this case, you get all the possibilities. You know, you don't get a concrete phase diagram. To get a concrete, this global phase diagram, you need a concrete model, concrete coupling constant. And then for different coupling constant, you may have a different phase diagram, but they all fit some selection rule, like a certain gapped phase can only be connected by certain conformal field theory. And so there's a constraint, there's selection rule. And we want to understand those constraints, those selection, but at this phase diagram level. And I'm hoping that the selection is very restricted, maybe unique actually. And so this is a kind of a thing we are trying to push. And actually that's also purpose, motivation I present this data. So there's a very concrete global phase diagram actually raised a lot of questions. And then we want to have develop a method and a way to understand this. This is the simplest symmetry breaking phase. And I thought we understand them 40 years ago. But now I realize that's there's still a lot of open questions. For example, this transition from S3 to Z1 is very puzzling. Maybe there's some paper I didn't know, but like I tried to search, I couldn't find anything. There's a lot of things about Toss model about the S3 to Z2 transition, but S3 to Z1, I don't see much. Yeah, please.
Right. So can we define the central charge, which is off the critical point or
Zero, off critical zero.
So in all,
all this, the black means zero.
All this means zero.
Zero, yes. So central charge is a very, very nice quantity to probe this to probe transition because it's zero in a gap phase. Then when you have transition, it jump up to be non-zero. So central charge actually describing the partition function that depend on shape of a space-time or space.
So can I understand that then there may be the difference in the height of the central charge along this boundary?
Yes.
Means that the maybe it count the how many fields are becoming conformal.
Exactly.
Field.
So central charge count how many gapless fields you have. If central charge equals to 1, you have one bosonic gapless field. But for the Ising model, central charge is 1/2. You have half mode, which actually is the fermion, Majorana fermion.
Right. Thank you.
But in some cases, you may get fractional power. So this is the 4/5. This is like 1.3. So well, that's typical in the strongly coupled critical point. You know, it's not described by free boson field. For free boson field, central charge is equal to 1. Yes.
I have a naive question. So between the S3 to Z1, you said the central charge cannot be determined. Like, assuming that it's continuous, should it be like really conformal theory or
Yeah,
like,
it's
can it be
conformal theory.
different? Then do you expect it to be unique? Like if I transit between the like different CFT, then I would expect central charge may change
Yeah.
along the parameters.
Yeah, this is a very good question. And usually we try to say central charge maybe is a fixed, don't change. And but this central charge is bigger than 1.3 or something along that. If less than 1, there's only finite number conformal field theory with central charge less than 1. Then we can just go through the list to see which one. This is bigger than 1. Above 1, there's infinite number conformal field theory. It's much harder. We have to do more works to determine which conformal field theory, because there's infinite choice. And the other two, the central charge is less than 1, so we know which CFT is describing that. So again, this is a question. So how do we get actual information to select among infinite number conformal field theory some particular one which is satisfy those extra informations? And if you only look central charge, it's not enough. There are too many degeneracies. So we need to know better. We get more data, more detail. Now, can we do that? How to do that? So that is the question. Yes.
So here at least we have 3 length scales basically, so corresponding to it. So can you have some data how the correlation length, I mean, the scaling as a function of, so
yeah, one could get that. It's but I didn't do this. Yeah, the data is there. In a sense, the width of this width depend on system size. So by studying this width of the central charge, and as a function of system size, you determine the coherence length.
So yeah,
so basically, is that in the black region, the coherence length is much less than system size. In this half height point, maybe coherence length is about the same as a system size.
Yeah. So so we have several types of, particularly near in the vicinity of some multi-critical whatever.
Yeah.
Some, which one is faster increase? I mean, depending on, so because I mean this is numerical calculation, which types of correlation lengths increase faster and depending on the approaching the direction. So
yeah, I think
I mean it labels in the previous page also so path dependent some nature of phase transition. When we have some competing several types of scales, so which one is faster increase and which one is less increase? I don't know. So
this is a little difficult. And there's several other parameters indeed, and each may play different roles. And maybe one can do this, but I haven't really, actually there's a lot of information from numerical calculation we did not extract. And we just know that there's all like this transition is controlled by this little phi, this little order parameter, and the coherence length of this little phi is you can read that through this width. And the coherence length of big phi is control this transition. I think from this width you can see that one.
Yeah, much away from.
And this one is actually. Again, we have similar issue. I think this is multi-critical, but not so sure. Yeah, maybe, but there's no other choice. Maybe it's multi-critical. But we also don't know which CFT. Again, that's another question. Here is multi-critical, which CFT describing this. The central charge here also about 1.3, and here also about 1.3. It's a little bit strange. Yeah.
So it's just the numbers are changing very smoothly.
Yeah.
So you must have some nice expression of central charge for any, I guess, point, right?
Yeah, suppose, yes. This is very interesting. This became a scaling function. That is a near critical point, you can plot the central charge shape in some scale invariant way.
Right.
So,
So
the
can I ask you-
curve from different states are all class.
Right.
And this function should have universal form, which I think, I'm sorry, I think in some cases people compute this, but I don't know in details. Yeah, this scaling function, in some special case, people can do the computation. I think for this case, people can do the computation.
Right. So just I was curious about the expression of that quantity, which really becomes the central charge at the conformal point, while it is 0 or something small number of the. So, do you have that expression for your numerical computation?
It's central charge. I don't know what's mean by expression, because here the central charge is just 1/2. You mean the expression for this whole function profile?
Yeah.
No, I don't.
Because you see that the things are not sharply moving discontinuously. It's
It's not
smoothly moving.
It's a
right?
smooth. There's a smooth curve.
So you must have some numerical way to compute this.
Yeah, numerically we have the shape, we have a curve.
Right. You do
But
have
whether I think in some cases we have an analytic expression of that curve, but most time we don't. Yeah, this is a very difficult issue to get this analytic expression of this shape. And for Ising model, we may have it, but for other, I'm not so sure. I think in this case, I think for Ising model we have this. This one we probably have, but this one I'm not sure. But again, it's a very, very interesting question. That is if you look at this numerical data, like experiments, that's raised a lot of questions. As a theorist, we should answer that. And but those simple questions, it's many of them are really open. We don't have answer. Yeah. Actually, that's my message. Try to present these results.
Just want to make sure this not so sure critical point. The time and space scale in the same way. So the dynamic critical space is for sure.
In the statistical model, we have some kind of auto rotation, so space-time scale in the same way. Yes.
Okay. Thanks.
Okay, I think we discussed a lot of issues here. So the Kingston-London theory is a classical theory, and actually we get this we got some wrong picture, and the quantum theory really present a very different picture. And this is seems to contradict with the standard thinking. So Kingston-London theory should describe a quantum critical point as well. And here I want to emphasize that we have a lattice model. The Kingston-London theory actually is a so-called mid-infrared theory. This is a field theory, but they are not a fixed point theory. And if you do the RG flow, the CFT is a fixed point theory. And so indeed, you're starting from Kingston-London theory, including quantum fluctuation properly, potentially you can get the CFT, you can get that. But exactly how to do that is tricky. We don't have a general method to do that. So what I'm really talking about is called a deep, it's a fixed point deep IR theory. So that is at the critical point, we have infrared theory which don't change under RG flow. That exactly describe critical point. Under that theory, we don't know. So therefore, the challenge here is to find this deep IR theory. And in many cases, deep IR theory is not even field theory, because usually in the quantum critical point, there's no well-defined quasi-particle. So there's no field that looks like a classically. Everything is strongly quantum mechanical, very strongly fluctuating. So there's no nicely defined field theory. So that's a challenge. So we don't even we know the answer, we cannot write them down, because whatever field theory write down is the wrong theory, it's wrong answer. And so basically that means that we need to develop a new formalism to even write down the answer, and not to mention how to calculate the answer. And so in the rest of my talk, I'll try to push this forward and to answer those questions raised by this numerical calculation. What is a CFT? What is general theory of this critical point? Seems to take a very long detour. we first study topological order, which is a totally different thing. Topological order is for gapped states. But actually, this topological order and the gapless states, CFT, are closely related. Because usually in CFT is a gapless theory. The gapless theory have a lot of emergent symmetry. And then we want to use emergent symmetry as a key to understand the gapless theory. And to do that, we want to understand all the emergent symmetry. And usually there's a lot of discussion of emergent symmetry. But mostly, people just study a particular emergent symmetry. The Z2, there's actual Z3, and the actual U1, things like that. Here, I emphasize that we want to obtain all the emergent symmetry. So that's an issue. When you have a gap theory, can you say what is a complete emergent symmetry for the gapless theory? And then the wishful thinking is that if you know the complete emergent symmetry, that may fully characterize the gapless theory. So this is kind of a program that using symmetry to fully characterize and describe a gapless theory. Okay, but here that sounds impossible because symmetry is some special property of gapless theory. The gapless theory is much richer than symmetry. But it turns out that symmetry is also very rich. There is a symmetry, anomalous symmetry, higher symmetry or higher form symmetry, anomalous higher symmetry, the algebraic symmetry. This is also called non-invertible symmetry or non-invertible higher symmetry. And there's an anomalous non-invertible higher symmetry. And in maybe there's all kind of things. Especially in recent years, we see a lot of symmetries. And then you may say, oh, that's just a game. Why? That's a weird thing. In condensed matter thing, you never have those symmetry. You just have a U1 symmetry for charge conservation. But actually, we do. That's precisely in the way I just said. When you have a low energy gapless theory, there's emergent symmetry. The emergent symmetry can be bigger than the lattice symmetry. In the lattice level, we may only have U1 or Z2 symmetry, but the emergent symmetry can be much richer. And it's well known that usually emergent symmetry are not anomalous. You may have anomalous emergent symmetry. And nowadays, we also know that it can be non-invertible or algebraic. It can be all kinds of symmetry. So actually, in condensed matter, we do need to study this generalized symmetry because emergent symmetry can be that general. Okay. So then this and to study this general symmetry, one somehow need topological in higher dimension because there are so many symmetry. The formulas became very complex and looks like only expert can do that. But there's a way that all the symmetry can be viewed as a shadow for topological order. So actually, topological order in one higher dimension is a unified and a systematic way to discuss all those symmetry in the same formalism. So after I realized this, now they almost refuse to talk about the anomalous symmetry because it's very weird and strange. And when you look from holograph point of view as a topological in one higher dimension, everything is clear, everything is simple. And then using anomalous symmetry, anomalous is it's really very strange, And so that's the motivation why we want to talk about topological order because actually topological order now can be a way to describe a generalized symmetry. Yeah. And then with this understanding for generalized symmetry, then we can using this low energy emergent symmetry to really characterize or understand the gapless states. So that is basically is a motivation for this. Yes, please.
So another connection between topological orders and CFTs is that CFTs live on the boundaries of topological orders kind of more directly.
Yes.
Right? Instead of this as a shadow of this, symmetry described by the topological order.
Yeah.
Are the two things, I guess there must be some connection, but the two are distinct concepts apparently.
Yeah. And right now I'm thinking the two are the same concept.
Oh, okay.
Yeah. The difference is the following. And you can see I'm from the angle of gaplet states with emergent symmetry. I want to include all the emergent symmetry. And that means I want to view this gaplet states at a particular topological order which describe all those symmetry. But in many cases, we study gaplet states only consider part of emergent symmetry. Then certainly this gaplet states can be viewed as a boundary of a smaller topological order, only describing this part of emergent symmetry. So that's the difference. So the two become the same if you think maximal emergent symmetry. So there's a topological order describing maximum emergent symmetry. And that makes the two the same. In that sense, emergent symmetry may be more powerful. There's maybe some hope to characterize gaplet states. I'm not sure it's going to work or not. I'm hoping it works. You know, even if it does not work, that means we're missing some information, something. Let me just work. You just add what we miss, then maybe this is going to work. Yeah.
Okay, so now usually when people say like there's a module tensor category which describes the chiral data of a CFT, but then but there's kind of the correspondence of the general structures, right? Like CFT has the primaries which correspond to the anyons of the MTC and so forth.
Exactly.
But sometimes you actually choose a specific boundary condition.
Yeah.
So there's kind of a distinction between like a specific system with a specific boundary condition and kind of the general correspondence of the structures. And I mean, so this I actually learned from some of your papers.
Yeah.
They're on non-invertible anomaly or something like that, right?
Right.
Is this connected to that? The thing about like taking the maximum possible?
Yeah,
MTC
that's a key. If you do not take a maximum symmetry, there's a lot of ambiguity. But even if a lot of ambiguity is still a big improvement, because usually we have ambiguity which is infinity. So if you have a maybe uncountable infinity, maybe improve that to countable infinity. So that's improvement. And but certainly here we want to maybe there's still ambiguity, but maybe just a few, you know. So if you know the emergent symmetry, a complete emergent symmetry, there's only a few choice of CFT which have that structure. And that's kind of a hope I make that you know, this indeed using symmetry to fully characterize gaplet states. It's sounds strange, you know, maybe not possible, but using maximum emergent symmetry of a gaplet states, maybe it's possible. So I think in Hanaji, for people in Hanaji, maybe I can phrase in the following way. That's you know, symmetry is a topological defect, topological defect surface. And basically what I try to say is that for the gaplet theory, if you know all the topological defects, the main wall, that may characterize the gaplet states. Yeah, that is the things we try to push. Yeah.
Okay, thanks.
Okay, so maybe we'll take maybe 5 minutes break, and we will switch gear to topological order in the next part.
Yeah. More questions?
Yeah.
So yeah, then let's meet. 5 minutes is okay for you?
Maybe 11:30?
It's okay for you?
Hmm?
Yeah, 11:30. Yeah.
11:30.
11:30. Let's meet 11:30.
Yeah, some little break. Yeah, I should have break earlier. Yeah, but this part take longer. Yeah, the point is that this those fancy stuff actually is try to answer those basic questions. That's the point I try to make. Is that yeah, we just symmetry breaking, critic point. That's a very basic question, and we want to answer whether there's an analytic way to to addressing that, to answer those questions.
Anyway, it's excellent to have lots of questions.
Yeah, that's great. Yeah.
Yeah, probably I guess that the communication a little bit wrong in the sense that I was not.
Oh, yeah. Okay. Yeah, we learn a lot from string series. Yeah.
Okay, so I didn't ask the profile of the C.
Yeah,
But
okay.
I was asking that actually, I don't know how to define the central charge for the of the while you compute. So what I was asking.
Oh, I'm sorry. Yeah. Yeah.
how to define that
Yeah. Exactly. And yeah, in the tensor network, one can do that. And so let me say that. Okay. And yeah, I'm sorry. Yeah, this is a very good question. So usually, in tensor network calculation, we compute the partition function, which depend on the shape and the size of space-time. But usually, partition function, the leading term is the energy density times space-time volume. That is a leading term in any quantum system. Then we can shift the energy 0 to shift energy density to 0. So we don't have this volume term. The next leading term will be this euro, will be this the partition function in a subleading term is what we have a so-called central charge even off critical point. So basically we just compute the partition function as a function of system size. And then removing this volume, this linearly dependent volume term. After removing that, the partition function basically is actually do not depend on the space-time volume, only depend on space-time size, shape. They do not depend on the size anymore. They only depend on shape. And we can extract this sublinear. We can extract sublinear term, and this is what we did numerically. Yeah.
It can be defined
in any point, exactly. Yeah, I'm sorry. Yeah, okay. It can be defined at any point. Yeah, it's really this yeah.
By looking at it along, like doing entanglement, taking the collision to read off like primaries or something.
Yeah, maybe I'm not familiar with this. And
I mean, well, I assume the way that you extracted this chart here was via the entanglement, but no.
That's much different. It's a transcendent strategy I just mentioned is in the tensor network we compute the partition function as a function of system size. And the leading term of partition function is e to the action. This S, the leading term is volume times energy density. That, and we subtract that out. It's a little like entanglement entropy. The leading term is non-universal. Yeah, okay. Yeah. So exactly. Yeah. So the leading term is non-universal. We remove that. The subleading term is central charge. And so in the computation, we just compute the partition function for different size, remove the leading term, the subleading term, whatever subleading term is defined anywhere. Not for any field theory can define that. Yeah.
Are there any other ways that you thought about other ways of extracting what those dimension operators are?
Yeah, there are other way. Yeah, actually, Nolan Center we have a spectrum operator also.
Really?
Yeah.
For this whole.
Well, the whole thing. Yeah.
Those look like they change along this one thing? Or
yeah, whenever we can compute central charge, we also have a scaling dimension. Again, this is a little bit technical. I won't explain here. Is that the tensor network calculator get a tensor. This tensor can compose into a matrix. The largest eigenvalue is central charge. The next eigenvalue is just a spectrum. It's H. Scaling dimension H. Yeah, so it's all there. So the only thing that there's approximation. I hope your matrix is more accurate, and then those numbers are better numbers. And in the best calculation, numerical calculation, is the standard charge can be determined of 5 digit or 6 digit. Yeah. Operator dimension is less, maybe 3 or 4 digit. Yeah.
But sorry, on this kind of
Yeah.
unidentified fixed point.
Yeah, that's very important. If you know the critical point exactly, you have that. If you don't know exactly, then you need a lot of effort to determine where is the critical point. Then certainly you just arrow there, and then the accuracy will be lower.
I'm just wondering, right, because on the phase transitions that are clearly minimal models, is obviously
Yeah.
the operator dimensions are fixed, but since you have a central chart that's above 1, it could depend on where you are.
Exactly. Yeah, there's more complicated. Yeah, the H is more complicated. Yeah. So everything is here. Yeah. Yeah. So listen, I'll try to go down. Yeah, I should switch to the next one. Let me see. Yeah, I need to switch the next. How to. Yeah, this is that one. Yeah. Yeah. Okay. That's it. Okay. Okay, so let's yeah, so here try to introduce a topological a little bit. And so at the beginning it's pretty simple. Let me just go through that quickly. And so we know that all the different phase matter is in a standard way described by this symmetry breaking result. But as we discussed in the last part, and so the key is that we have a symmetry group of Hamiltonian and symmetry group of ground states, and this pair actually describe and classify the phase of matter. Basically, the phase of matter. Let's see what it is. Let's get some more. Okay, so the phase of matter, is that working? Hello? Yeah. So the phase of matter is classified by a pair of group. And but however, when you study heavy superconductor, and there's a spin liquid became popular. So we want to we say the spin liquid, and as a parent states. When you're doping the spin liquid, there's a boson condensation, a holon condensation. That's one way to understand the heavy superconductor. So in the early days, is like in 1980, 1990, beginning 1990. It's really what I say. Maybe I should say the golden time for theorists, because nobody knows what is High-T theory. So whatever you create, you create thought is you can publish it. So actually, there's a lot of crazy theory from that area, and so this spin liquid is a wonderful crazy theory. But there we have an issue, how to characterize the spin liquid, because in spin liquid, orientation of spin is random. So it's like there's no symmetry breaking. There's nothing there, and so how to characterize this? And then there we come up with the idea. Maybe even when the spin orientation is random, but this combination is a spin singlet, but but the break time symmetry. If this outer parameter is non-zero, then we have a spin liquid which break time symmetry. Because at that time we're still thinking to characterize the phase, we should describe the symmetry. So using this. But then we quickly realized that actually there's several different phases have the same order parameter. They look very different. So that's give us some kind of a doubts. That's maybe order parameter is not enough. And there are different phases with same symmetry breaking. Then after spin liquid, so for me, I start to learn quantum Hall state. I should learn quantum Hall state before spin liquid, but for me, it's in the wrong order. Then I start to learn quantum Hall state. I find the quantum Hall state have the same issue. That's in the two-dimensional electron gas, we have a lot of quantized Hawk dust and a lot of plateau. Those should be described at different phase. But all those phases have the same symmetry. The sample is very dirty. Actually, the dirtier sample have a better defined plateau. Then we have randomness, then there's no symmetry. The time reversal is broken because of magnetic field, so there's no symmetry. And without symmetry, we still have this a lot of phase. So again, same issue, using symmetry breaking, we cannot describe a quantum Hall state. So therefore, we think a chiral spin to the quantum Hall state must have a new kind of order. So we call this new kind of order, so topological order. And so what is topological order? So there's three kind of quantum matter: the trivial, interesting, and the messy. Trivial one is the one have energy gap. We don't have energy gap at the low energy below the gap. There's nothing. So that means trivial. Okay. The interesting one is like super fluid. Basically, it's like it's a gapless state with a linear dispersion relation, like a CFT. That's the interesting one. There's a messy one, is like a Fermi liquid or metal. You have a Fermi surface with a lot of low energy excitation. It's really messy. And actually, topological order belong to this trivial class. Okay. So we studied these trivial things for 30 years. I don't know why. But the point that even trivial things are not, it's actually very interesting. It's not that trivial, it's interesting. But here, interesting have another meaning, means that I just mentioned. The interesting in the sense that it may give us a systematic and a classifying understanding of this interesting quantum matter, the second class. So here we try to go from first class trivial one to the second class interesting one. And maybe after 30 years, we can go from the interesting one to messy one. So that's a kind of a thing. But however, in condensed matter textbook, we do messy one first. And which is interesting fact. So the issue is that, when you have this below energy gap, there's nothing, wide anything. But actually, the grounded degeneracy have its own dynamics. Because below the energy gap, we don't have any excitation, but we still have a grounded degeneracy. So it turns out that for chiral spin state, or maybe for the quantum Hall states, the grounded degeneracy depend on the topology of a space. So grounded degeneracy on the torus of the genus force is different. For the gap system, we have finite energy gap here, but this grounded subspace is nearly degenerate. Yeah. So this non-trivial dynamics of degenerate ground states. The dynamics means it depends on spatial topology. May give us some kind of indication or measurement or definition of the topological order. So that is a kind of a topological order. And the most important thing is that the ground degeneracy is topological. Usually when you say the degeneracy, you say, oh, that's because the symmetry and the non-trivial irreducible rotation gave us a degeneracy. But that degeneracy is exact. The topological order degeneracy is not exact. Not only not exact, it's robust against any perturbation. So it's something really interesting. That's so at any dearths, we still have the degeneracy. So therefore, this is really topological degeneracy. The degeneracy can only change like this. If you close the energy gap, then open them again, you may get a different degeneracy. That's like a continuous phase transition, which is changing ground degeneracy. And that's like a topological phase transition. Or you could have first order transition with minimal switching. There's one state with topological order, switch with another state with no topological order, then there's a transition. And these two things cannot happen. You cannot just degeneration just cannot change by itself. Yeah, this is really robust. So So then one asks, what is the origin of degeneracy? Why we have a degeneracy not coming from symmetry, but robust against any perturbation? This is kind of strange. It should be, in a sense, looks impossible. But how do we have that? Then many years later, we realized that, when topological was introduced is 1989, and at that time, the quantum information entanglement is not very popular, so we didn't think of that way. But in the 1990s, the quantum information science take off. Then people start to think about the quantum entanglement, even in condensed matter. And then we realize that actually the topological order have this topological entanglement entropy, which is a sign that maybe this topological order or this ground degeneracy, topological degeneracy is related to the entanglement. It's actually the property of entanglement. So indeed, entanglement have this property that if you don't know every part, you still do not know the whole. And so just this example is that suppose we have this two spin, this up plus or minus down. We have two different wave function and two different whole density matrix. However, if you look at this density matrix, not for two spin, but only for the first spin, by doing some partial trace. Okay, that's an entanglement density matrix. These two density matrix produce the same entanglement density matrix, identical one. Yeah, the local Hamiltonian only see part of the system, can only detect this entanglement density matrix for that part. But the global wave function can be different. We may have a different global wave function such that every local part, every local entanglement density matrix is the same. So this becomes a notion of this locally indistinguishable many-body states. We can have a different orthogonal many-body states where every local part is identical. So this is really the property of entanglement. And so this is a very, very simple example of this kind of slogan. Knowing every part, we still do not know the whole. So this is the reason behind which we have a topological degeneracy, because the Hamiltonian is a local term, and we cannot detect this global difference. And historically, at the beginning, we don't know entanglement, so we do not derive or argue for the topological degeneracy using this argument. At the beginning, the argument is kind of very formal. It's a field theory. There's Chen-Simon theory, and there's a global gate transformation, or maybe, not global. There's certain things which is some global transformation, which globally is non-trivial, but locally gauge, some formal argument like that to argue degeneracy ground state, which do not depend on impurity. But I think the microscopic reason is this special property for entanglement. So I think we talk about this, so let's skip this. Okay, so here is that. So let's explain why entanglement is important. Why the ground degeneracy coming from this long range entanglement.
Yeah. I think. So in the previous page, so how, as far as I know, how can you say some ground state degeneracy from entanglement entropy? As far as I know, the topological entanglement entropy, that piece counts the total number of dimensions of whole excitations, not the ground state degeneracy. No. So I'm confused.
No, it's different.
What are you saying? So what?
Yeah,
do you mean?
This is just this is just some kind of thought. Okay, they are not directly related. But the point I try to make here is that before this topological entropy, we do not even think about entanglement. We have this degenerate ground state. We have some topological quantum field theory, or there are some other things. But we don't even think about entanglement. But after this, we start to realize entanglement actually is important, should play a central role. Then we start to think about entanglement. And So they are not direct related, but they reveal that the entanglement play a central role in this kind of physics. And then, so this motivates me that was thinking about entanglement. And then the story I try to tell is that thinking about entanglement, what do we learn? So this is the kind of switching, as I mentioned that, nowadays we see the interaction of many different fields. At the beginning we talk about condensed matter physics, and now we find the answer to the question we have actually coming from quantum information science, and this topological topological degeneracy actually coming from string theory. Is topological field theory play a big role in arguing, we have this topological degeneracy, which do not depend on any impurity, And so there's an interaction between many different fields, things play a big role here. And here we want to understand this degeneracy and the entanglement and their relation. Here we want to do things more carefully. What do I mean by gap state? It's a very tricky question, actually. It's obvious this is the gap states. But why you call this gap, they do not call this smaller one gap? That's also a gap. Okay, then you need to take a limit. So actually, the concept of gap phase or gap state is not even a concept for the single system. It's a concept for the sequence of system, taking the limit of a large system size. So immediately it's become really weird. You have some quantity which is property not for the single Hamiltonian, but for the sequence of Hamiltonian. Then there's a lot of issue here. So here, that's to say, I need to take a sequence of Lagrangian, and the gap of the property is a property of the sequence, not even for the single system. Okay. And then the first thing that but certainly for different Hamiltonian, we have different ground state, or more precisely, the different ground state, the subspace, the subspace spanned by these two states. And then we say that the two gap systems are similar if they can be connected by this adiabatic deformation. We have a Hamiltonian depend on the coupling constant G prime. We change G prime smoothly if this one ground state can change to another smoothly without energy gap closing. We say they are connected. And this adiabatic evolution can be thought as a sequence of a small time step evolution. And but this on a very single time slice, we can write Hamiltonian as several parts, such that the local operator in each part they commute to each other. Because in general, local operator may overlap; they do not commute. But we can write in the different parts so that this box interaction. So certain this box and that box do not commute, but we can write them in two layers. Then each layer gets commuting operators. And this way, we realize that, I should put I there. I forgot to put I there. So actually, the backtime evolution can use a layer of unitary revolution, but generated by the local unitary operator, which are independent. So each box is like a local unitary transformation. And this in quantum, why we do this? Because people do this in quantum computer. So that's a gate, the local unitary transformation is a gate. So I'm plotting a quantum circuit. We're doing this local unit transformation and the changing states. So then we can say that this equivalence relation between two phases which are equivalent means they are connected by this adiabatic evolution. Now I can rephrase that they are equivalent because they are connected by the local unitary transformation. So that's kind of quantum information way to say the same thing. So this is a way to define this gap states. If you don't have a gap, we may have a trouble. We have energy gap. This adiabatic evolution is a good notion, but gapless states, yeah, we have difficulty to use in this way to even define the phase. Yeah, so that's demonstrate how hard is the gapless states. Okay, so now here I'm doing a little bit detail.
Then,
yeah,
so what does it mean, gapless phase? How can you say these two gapless phases are equal? So
yeah, this I don't know. Yeah, yeah, indeed, give this definition for gap phase really raise this question. We should have a similar general understanding for gapless phase. And I haven't really think very, very carefully about this, but I'm thinking something like that may work. Because for gapless phase, basically this we can view gapless phase as a gap phase, but with the level spacing is 1 over L. We have a level spacing 1 over L means that we may need to do the transformation more slowly. Actually, there's one thing I'm kind of very quick here. For gap phase, you just need a finite number of layers of unit transformation to do connection. That's called that definition of gap phase. We call the finite depth quantum circuit. If two gap phases are connected by finite depth quantum circuit, they are equivalent. So this finite depth is associated with a gap because depth is like a time direction. When you have a gap, in time direction, we don't need a very long time evolution to make an adiabatic connection. But for gapless, you have to do this slower change. I don't know the answer, but right now I'm guessing maybe we allow polynomial depth circuit or something along that direction, or maybe log. I don't know. Yeah, I'm just making a wild guess. But something along that direction may allow one to define the phase of a gapless matter. Yeah.
I think your guess is very likely correct. There's some results indicates gapless state coupling is not necessary that terrible.
Okay. Yeah. Thank you. Yeah.
So is there analog concept for depth of this circuit to field theory? So what is so I want to translate the depth of this unitary circuit to, in terms of some field theory language. What is it?
Yeah, it's basically adiabatic evolution. Because when you do the evolution, you hope the evolution is slow enough. Means the duration of evolution, like t, we say 1 over t should be much larger, much less than the energy gap. Yeah, so for gapless states, maybe one need to even slower and something. Yeah. And so here's but however, what I described a moment ago is not very precise, because we know the gap phase is not single Hamiltonian, but in the previous slide, I'm still pretend we have a single system, single Hamiltonian, single side, and do this adiabatic evolution. We should do this, for each side we do this local unitary equivalence. So these two sequences are equivalent, and that's define the system. But once you look at this picture, it's very strange, because it's possible that maybe for this size we have a Hamiltonian described quantum Hall state. For that size, we have Hamiltonian described antiferromagnetic states, because the different sides are totally disconnected. And especially when you have a translation, you have a system without translation symmetry, then these different sides can be pretty arbitrary. Certainly, this works if you have translation invariance. Then different sides are very related. But without translation symmetry, we couldn't do that. And But however, topological order do not need any symmetry, so including translated symmetry. So how to define topological order without translated symmetry? Yeah, there's a problem. Yeah. Okay, so we want to add a line which connecting different sides of the system. So how to do that? So there's one way to do that is that we add a product states. You have a states with certain spin. You add more spin, but the more spin in the product states. Then you make a bigger system. Then you do log unit transformation to see whether this the original states with additional product states, whether they are log unit equivalent to this bigger system or not. So therefore, adding product state is part of the equivalence relation. This allows us to do things horizontally. Then everything is connected. Actually, this idea is very much like people mathematicians did in fiber bundle. You can stabilize the fiber bundle by adding this trivial bundle. So this basically is that kind of thing. Okay. And so in this way, we can define this topological order. And here I want to define this notion of a liquid. The liquid means that the ability to dissolve these product states. It's like the product like salt. You put the salt in the water, it dissolves and become invisible. So this notion of a liquid, yeah. And so basically, from this notion, the topological order is a gap the quantum liquid phase. Yeah. Yeah, you may ask why you add the liquid. It's a topological is a gap the quantum phase. That's fine. Why you say liquid? The interesting thing is that there's a non-liquid states. No, there are some states which is a gap, but these gap states are unable to dissolve product states. Some weird things like that. So yeah. It's not randomized. It's just actually this again we are learning from quantum information. We have a many-body entanglement in a big system. Entanglement have many pattern and structure. One way to describe this entanglement structure is to ask, can they dissolve product states? Whether adding product state to this entanglement make it looks like it's same type entanglement, but for the bigger system. And let me give you some example. You say there's counter example, then you understand appreciate this better. The counter example actually is very simple. These first two examples just trivial. We have a layer of a two-dimensional topological order. We have a layer of two-dimensional topological order. Each layer, if you add a product on each layer, then you can dissolve them, make a layer bigger. But you cannot make a vertical size bigger. In that case, you need to add a product state between layers. But the product state between layer is not topological. It's product state. It's kind of trivial. There's no ground state DNA for the product states. So if you do add a product state between layers, then you indeed get a bigger three-dimensional system. But it's wrong scaling because when you make a system bigger, the layer became more and more dilute. You don't have same density of layer in vertical direction. Because intuitively, we say the scaling of this system will make a bigger system. The layer density should be the same. Just system size bigger. You have more layers. But adding layers is not adding product states. The topological order is opposite the product states. And so it really means that this kind of layered topological order, although from long distance looks like a three-dimensional system, but there's a hidden foliation in a 3D system. It's there, which defies renormalization. If you want renormalization, you make a bigger system. This UV structure persists. Still affect the infrared property. You can see this is like UV IR mixing. Yeah, for example, like the infrared property like a ground state DNA. And the ground state DNA in this case depend on this M to the LZ. M is degeneracy for the single layer. When you have M layer, it's just M to the LV. But however, if you're changing boundary condition like this, you say this layer here, but join the next layer, the next one. And this one actually effect only one layer. So that this kind of boundary condition degeneracy is M. If you do two twister, is two like effect like two layers is M squared. So you can see the ground thickness is invert property, but they depend on the detail of this UV structure. So that's like a UV-IR mixing. So this picture really means there's another type entanglement which are unable to dissolve product states. So this is called non-liquid states. Yeah, this is non-liquid state. Yes.
So these well, I guess, but both for the liquid and non-liquid states. So are we really talking about the sequence of systems here in both cases, or?
Yeah, the thing that indeed when I say dissolve layer, because we have a sequence of systems getting whose size getting bigger and bigger.
Right.
And we ask whether the two systems with different size are they differ by product states or not?
Right. So for the non-liquid states, we still have a sequence of systems related by
maybe
in product states.
Maybe this is a question to answer. Is that so? The quantum Hall state example I have is that to go to one side to another side, we not only need to add the product states, we also need to add another layer itself. It's two copy, you know. So adding product state is not enough. We have to add system self. And so this is called S equal 2 because every time you double the system size, you need to make a two copy system together. Yeah. And there's another more strange one. So when you increase system size, you need to add something, but the thing you add belongs to the second class. So something really weird, you know. This one is simple. Every time you increase system size, you add the product states. Here you have to add the system itself. And here you add something which belongs to second class. Yeah. So those are examples of non-liquid state. And this became very popular because this is called a Fraction order. And in high energy physics, it's also interesting because those kind of states do not have quantum field theory description. I think do not have a usual quantum field theory description. And recently, this Natty Seiberg, they tried using a special quantum field theory with a discontinuity or something, then tried using that kind of generalized quantum field theory to capture this kind of fraction order. For example, for this topological order I just mentioned here, there's a layer. Each layer you can see is like transformation theory. We all have a 3 plus 1 dimensional system, which is a composition of many layers of transformation theory. This is very hard. So basically, it's quantum field theory with infinite number of fields. Then it's not the usual quantum field theory because you have infinite number of fields. Yeah. So that is the facing what we are facing. But this kind of thing are there.
Actually, just one more question. So actually, just to clarify, so if we have that non-liquid state built out of layers, so but if we are given a specific number of layers, like just n, fixed n, then okay, it is some state, some system, right? But to say it is non-liquid, what we mean is that we have the sequence where we are giving this
sequence which n changes. Because if you fix the number of layer n,
right,
you are talking 2-dimensional system. But here we do 3D system where in vertical direction it also scales.
Right. Yeah.
And the scale to infinity, then the number of layers should scale to infinity.
Right.
But the changing number of layers cannot be achieved by adding product states.
Right.
Yeah.
Okay.
So this layered structure is intrinsic. That's UV-IR mixing. The layer structure is UV property, but it's influence infrared property. Yeah, please.
I have a question about the generalized local unitary transformation. So I guess that you can use this transformation to relate the quantum states for different n number states. But now I'm confused because if I consider different n in number of Hilbert space dimension is different.
Yes.
How do you relate them?
Yeah, we add in the product states.
Okay. So you add the, but it
you increase dimension of Hilbert space, but adding the product states.
Okay, so you increase the number of
Hilbert spin. Yeah.
Oh yeah. Okay.
Yeah. Then after you adding product states, then you do local unit transformation to see whether it's related to the one which seems no product states kind of dissolve into the background. So you can see these two systems have same size, but can we using local unit transformation to dissolve the product into the background? So it looks like the bigger topological order. Yeah.
So okay, let me ask one more. Usually we can, if we just use a local unit transformation, we can understand what the entanglement variable we need.
Yeah.
So, but what is the useful thing here for generalized local unitary transformations?
No, it's connecting the system with different size. So
Yes.
you can take a thermodynamic limit.
Yeah, but I can also, but why do I need to connect these two different n? Because
the reason is that we are talking about the quantum phase, which require us to take thermodynamic limit.
Okay.
Yeah, so I'm describing this limit more carefully. Usually in condensed matter, we just say we have a large system. we don't think very carefully how the limit was taken. And here it's just we do a more careful job.
So
the funny thing is that if you really do this very careful job, you will discover fractal phase by just doing this analysis. Yeah.
Okay, so your point is that you want to begin from the finite dimensional Hilbert space, then how to take a infinite.
Exactly. Yeah.
Thank
you. How to take a limit? Actually we try to take a thermodynamic. Yeah, this is what we discuss here is that we take a thermodynamic limit for quantum system in a very careful way. Try to recover all the subtleties. Yeah, that's and then we did this subtlety. Okay, and so let me see. Okay, maybe just finish this part. So topological actually is a part of a long-range entanglement, and so it's really, so here I already assume the system can be enlarged by dissolving system. So here I only concentrate on the local unitary transformation. Okay. So the point is that if we have something which connect to the product state by this local unitary transformation, more precisely by finding the layer of a local unitary transformation, then we say they are short-range entangled. Because product state have no entanglement between different qubits. If you have a finite layer of a local unit transformation, which only covers 7 range, then we use this to define short-range entanglement. Then the long-range entanglement is something not that. Then from here, it's clear that we're using the same local unit transformation to define the long-range entanglement and to define the equivalent class of topological order. So from here, you can see that the non-trivial topological order means it's a long-range entanglement because it's not in the same phase as the product states. It's some other phase. So this really, I try to define what is a long-range entanglement. But certainly, we have a long-range entanglement state which are not connected to the product states. Another long-range entanglement state which is not connected to product state. But among themselves, which may not be connected. Certain every short-range entanglement state are connected. So short-range entanglement only belong to one phase. But the long-range entanglement may belong to different phase. And so this is another way to say that this long-range entanglement characterizes topological order. Yeah. So that is so this really says that this long-range entanglement is a microscopic mechanism to have a topological order. For example, we have a superconductor. We say, what is the mechanism to get a superconductor? We say electron pairing and boson condensation. Then you actually ask similar question. What is the mechanism, microscopic mechanism to make topological order? We say long-range entanglement. But certain long entanglement a little bit abstract, we need to have some more concrete calculation of long entanglement to say to help us to design the Hamiltonian to make long range entanglement. And so maybe let me just say that when you have a symmetry, this concept of long range entanglement can be generalized to the system with the symmetry. When you have a symmetry, then the requirement that this local unit transformation like a Hamiltonian evolution, they should respect symmetry. This evolution operator should respect symmetry. So therefore, we have a less equivalence relation because the equivalence relation is more restricted. When you have a less equivalence relation, you may have more phases. And that's what happens. Yeah, please.
I want to figure out your definition for low range and short range entanglement state. So let me go back to the story of the LOCC.
Yeah.
For the three qubit physics, we can use the LOC local unitary transformation to get the two kind of states.
Yeah.
I think it's correspond to like you say that the local unit transformation between the product states.
Yeah.
But if we use this, so what is long range there?
Yeah, we have finite number of qubits, the things are very different. And so indeed here we want to classify entanglement. But this entanglement is so-called many-body entanglement. Actually, it's the infinite number of a system, infinite size system. And so the pattern is, you will have three qubit things like that. It's a very good example. There we know there's a different kind of entanglement, you can classify them.
Yeah.
But we have even number of qubits. It seems very difficult, but the classification will be different.
Okay.
And here it's kind of abstract. It's we try to argue there's something there. We don't know quite what it is, what is structure. I just say, oh, there's a long entanglement. But we don't have a symbol or we don't have an understanding or intuition for that. We can only say this is A, that's a B, that's a C, with no information. But we wish, later we have a more informative labeling, So this pattern like a square lattice, a triangle lattice, we can see them. But later I'll try to develop this more quantitative way to describe this long entanglement. But indeed, it's not like this eigenspace problem when you have finite number of qubits. But this is more.
So
and then we'll say, so it seems very abstract. So what is this? If you ask me, I say a category theory. I should answer for this category theory. So to really have this class of entanglement, turns out to be some category theory can describe this.
So do you answer that only when the number of Hilbert space dimension is infinite, then we can discuss a long range entangled state?
You need a very large system.
Okay.
This concept do not exist for any finite system.
Okay.
So it's a really thermodynamic limit.
Okay.
Yeah.
Okay.
So that's different from the quantum information discussion. We will have finite number of qubits. There's a lot of non-trivial results, but it's different thinking. Yeah. Here really is infinite system. Can we get something?
Okay. Okay. I understand. Yeah. I understand.
So
Thank you.
Let me ask. So how the concept of long range entanglement different from the absence of local gauge invariant local order parameters?
Okay, I don't know because you can say when you say gauge, it's that's part for gauge theory. But here we just have bosonic system or qubit system. We don't have gauge structure. So, but indeed, what you said is right. That is there's some order, there's some other parameter, but not like a local operator. In the gauge theory, the gauge invariant operator, this local operator, some extended operator. But here I try to define things using quantum information setting. And
Is it
at the
different?
moment, we are not clear what is other parameter, but maybe next lecture, there's some more concrete model. You start to see there's some other parameter. Yeah,
I see.
but those are really history. Because many-body entanglement is a new phenomenon. We just have no clue how to describe them, and we just do whatever we can. But at that time, we somehow working interact with the quantum information people and try to borrow the language of quantum information, like a finite depth quantum circuit, to describe this entanglement, to describe this thing. And I think later, actually, there is a more familiar notion, familiar to field theory, and which we can also have a similar picture, but from different angle. But let me finish this part. We have a symmetry. We have a less equivalence relation, but the more phase diagram actually is really this. That is we have a symmetry. Even short-range entanglement can belong to different class. They are not connected by symmetric local unitary. So that's really this picture. That is if you're using the non-symmetric local unitary, then these two states can be connected. But however, if you restrict yourself using symmetric local unitary, then they are not connected. So this is called the symmetry protect trivial state SPT states. We kind of debate for a long time whether which is the call, because these two states are connected by local unitary. They both belong to short entanglement, should be trivial, So maybe it should be called the symmetry protect trivial states. But however, these kind of have been studied before, have been named topological phase. So calling them trivial may be implied. So we call them topological. Okay. So but anyway, they have a abbreviation. It's the same. So finally we get agreement. Actually, I can argue with Zheng Chen. So I prefer this SPT. He prefer that SPT. So but anyway, it's both SPT, so it's okay. And certainly in the long-range entanglement side, there's a similar thing. Originally, maybe the two long-range entanglements belong to same phase. Maybe with symmetry, they belong to different phase. So this is really the picture from quantum information point of view. From quantum information point of view, this gave us this kind of a different pattern entanglement. It looks very rich, but at the moment, looks like very empty. There's nothing there. And the trouble is that using quantum information, I try to argue, yeah, there's this kind of structure, but there's no quantitative description of the structure. And wish you have something more quantitative, like something like triangular lattice, square lattice, something much more descriptive rather than just A, B, or they are different. So that's a remaining challenge, how to get the more quantitative description. So in the next lecture, we'll continue this. So we'll study more concrete model to do that. And then we find that there's a way to analyze topology order using higher symmetry. And then after that, we'll do the more abstract macroscopic description. Again, it's a more quantitative description of topology order. But there, I'll try using the category theory. And so basically, category theory is a more quantitative description of this kind of structure. This structure only defined using entanglement picture or quantum information picture. But the mathematical answer, quantitative description turned out to be some kind of category theory. Okay, so I should stop here. Yeah, I'll kind of over 4 minutes.
The talk is open for question. Yeah.
I'm very sorry. After you explain a lot, still I'm lost. What's the precise meaning of product state or adding product state?
Yeah. I think it's right, and yeah, it's here. So
So
you can see-
what's the difference between product state and the original local state? You specify the total state can be described by tensor product state.
Yeah, it's
right?
I think here. Suppose this phi ni
Yeah,
is some kind of complicated wave function
right.
for the system size with ni spins. Then phi ni plus 1
Right.
is a very complicated wave function for a bigger system with ni plus 1 spins.
Okay.
So usually we cannot compare to this wave function because they even belong to two different Hilbert space. One for the ni spin, another for the ni plus 1 spin. So
you just increase the system size.
But how? You already have given wave function.
Yeah, given wave function, you just
by increase system size. How you write down new wave function with a different number of spin? You could write down arbitrary another wave function, but that's not related to the previous wave function. So there's difficulty.
Right.
Yeah, you can write down the arbitrary wave function for the 3 variable, another arbitrary function for the 5 variable. But to say how they are connected is very tricky.
In principle, but
Yeah.
usually when we increase just the system size, we use basically same wave function. Just
no, what do you mean? It cannot be same because
All right.
your function with different variable.
Okay.
What do you mean by same?
So what is your recipe then?
So
here?
usually, I understand. Usually, what people do is following. They don't increase using same wave function. They're using the same Hamiltonian.
Okay.
But the same. What do you mean by same Hamiltonian? We have different terms.
Right.
When we have translation invariance, then there's a recipe to increase system size.
Right.
And we call they are same Hamiltonian, even though but the mathematicians are really different Hamiltonian, different operator with different dimension. Why you call this a matrix with different dimension, same matrix? But our physics say, yeah, they are same matrix, even they have different dimension.
Okay.
But because we use translation symmetry. But however, when you don't have translation symmetry, you have trouble. When you increase the Hamiltonian size, maybe the part you add is in the anti-ferromagnetic states.
Right.
The original one is the ferromagnetic state.
Right.
Then it's a crazy thing like that can happen. So we have trouble.
Yeah.
And here I do not talk about, I can do that with Hamiltonian version, but here I'm using grounded version. So basically, indeed, we have a issue that we want to increase the grounded size. It's for physics easy to just increase the size. We do that all the time, but the precise definition is pretty tricky. And here, what we do is following: is that so we have a very complicated wave function for the one side, for another side. Then we tensor product with another state, which is a product state. The product state is something like that. Just all spin up. Then after tensor product, then these two wave functions would belong to same Hilbert space. Then we can ask whether they are connected by a unitary rotation or not. Otherwise, we cannot even do unitary relation. And so this is what I try to say: that dissolve the product state into the background. When you do this, you still have this. You have a original complicated wave function, another product on top. Then when you do local unitary, then you can dissolve this product state into this more complicated wave function with bigger size. So this is the way to do this to take thermodynamic for quantum system.
So then, how do you choose your product state?
Any product.
Any product.
Because the local unitary transformation can rotate any product state to any other product state. They are all connected. So
basically, the function or the role of this product state is just shuffling.
No, to increase the system size.
Increase, but you also mixing.
Mixing is done by the local unitary transformation.
I see.
So the two steps. One, you just increasing system size by adding something definite. But when you're adding something definite, you have two systems put together. Then you're using local unitary to mix them, scramble them to make it look like the same system as before. So this is just a, you're completely right. We just say increase system size, that's it. But to the mathematician, it's more precisely one need to do this. That's what we mean by increasing system size. So this is the meaning. Actually, it turns out that there are systems which we cannot increase their size this way. We have to engineer some other way to increase their size, and that's reflect a different pattern of entanglement. So this fractal topology order is belong to this second type. So this type we call the liquid. It's very funny thing that the Fermi liquid is not the liquid.
What is it?
It's a S equal 2. It's belong to in this paper they say it's belong to this type. Yeah. If you dissolve product state into Fermi liquid, the Fermi surface will shrink to 0 when you take synthesize in the infinity. So it actually belongs to this kind. So actually entanglement structure in the Fermi liquid is not a liquid. So actually Fermi liquid is not described by quantum field theory. If you write down this effective quantum field theory only for the Fermi surface, is this effective field theory is not field theory.
When you say some system is not liquid, that doesn't mean also it's solid.
No, it's not a solid. So here I'm using this definition of liquid, dissolving this product state. If you define liquid in this way, you get a funny result. The Fermi liquid is not liquid. So maybe we should not call this. Maybe this is bad words. But unfortunately, sometimes we just using bad words, so causing a lot of confusion.
Okay, thank you.
I have a very naive question, maybe short. So relating to your first part with the talk, and then the local unitaries are connecting the different states.
Yeah.
Would you expect the classification of the critical points is the classification of the unitary circuits, which may go like a system size? So if I have a classification of unitary circuits, then maybe that gives you the classification of the CFTs and
maybe, yeah. So basically, that's really try to generalize this kind of circuit definition to gapless system. Can we define the gapless system, gapless phase in a similar manner? If yes, then we probably
look at
can formulate a classifying CFT in this more rigorous way. Yeah, I think I should read some papers that look at that some results say this. Yeah, there's a way to do similar thing for gapless system and define gapless space in this more careful way. Yeah.
Okay. Yeah. Thanks.
Yeah.
Okay, I have a question for this liquid phase case or your local unit transformation. Okay, if I take the finite n case, I expect that you can define anything. In other words, I think the algebra is correspond to the type 1 formula algebra. But if I take the thermodynamical dynamical limit n up to infinity, should I expect that you lose the pure state?
I don't know. Yeah, but this but indeed this von Neumann algebra type 1, type 2, type 3. I heard about that, and I think it's very relevant. And I'm planning to learn that.
Maybe you.
But however, I try to using a approach which only deal with a finite system, and then during the process of picking infinity, then I try to see some structure. My understanding from my very limited knowledge of von Neumann algebra is that von Neumann algebra has a way to deal directly with the infinite system. But then a lot of concepts get changed.
Yes.
And so in some sense, von Neumann algebra it's an amazing structure which kind of directly deal with infinite system. Maybe a lot of questions we are interested in. Yeah, and as I mentioned, I want to learn that, and but I haven't done so. But on the other hand, I try to say I will try to go things slowly. I mean, I understand the finite system, and I try to see this structure of a normal algebra, like type 2, type 3, or things like from finite system by taking limits.
Yes.
And whether, so this way, that maybe you can say that's maybe my plan to learn this Van Norm algebra using the taking limit very carefully.
Yeah.
And actually, the later you'll see that we introduce so-called the patch operator, really trying to do this in this fashion. But indeed, yeah, nowadays I really feel this Van Norm algebra, this kind of structure, is actually going to be very useful.
Yeah, I think it's okay to consider the finite system first and take an infinite n in the end.
Yeah.
For example, we can consider one example to the Young-Mills theory on a torus.
Yeah.
In this case, for the finite n, I mean finite n is un.
Yeah.
And this theory is due to some fermion theory
Okay.
on line, of course, because of fermion, so it's must be type 1. But if you take a large n limit, then you can define a trace operation, then the algebra becomes type 2-1. So it's fun to say.
Okay.
But for this case, from the understanding of polynomial algebra, we know that there is a loss pure state. What I mean loss the pure state means that the pure state is not normalizable.
Okay.
But because if you consider non-normalizable pure state, it's fine.
Okay.
That is what I mean. Okay. But
Yeah.
but
this is really interesting. Yeah.
yeah,
Okay.
but here I want to answer the question because I expect that you want to claim that long-range entanglement is similar to a spontaneous symmetry breaking. So some strange thing may happen only when you take a large n limiter first.
Yeah.
So I want.
So indeed, you're completely right. In the next lecture, I will present that picture. And so this story about that, for a while I kind of resisting that picture because as I emphasized, topological order have a character which are robust against any perturbation which can break any symmetry. So when you say the topological order can be understood as a spontaneous symmetry breaking, you need to assume there's a symmetry at the beginning, then spontaneous breaking that gave you topological order. Actually, this picture is correct. When you do have a so-called higher symmetry, the spontaneous breaking of higher symmetry indeed gave you topological order. But on the other hand, there's a little strange that is even when you break higher symmetry, you still get the same topological order. So actually, both pictures correct, but with a different emphasis.
Okay.
But on the other hand, when you say it's an order limit, that's also true because you can break symmetry at the lattice level. Then there's an emergent symmetry at the lower energy. Then this emergent symmetry is spontaneously broken. That's give you topological order. So this may be a more complete picture. If you want to use a symmetry to describe the topological order, the symmetry is emergent, then became spontaneously broken.
Okay.
Yeah, and that's very much like this different way of taking order may have things like that. Yeah, it's really completely right intuition.
Thank you.
Yeah.